Our first presenter today is Eric Zorn. Eric Zorn is a graduate of our department over in geology and environmental science. We're excited he's going to be speaking. Right now he works with DeGoya and Gray. He's going to be speaking on the use of small unmanned aerial vehicles to evaluate freestanding rock slope stability and assess performance of rock bolts on inaccessible slopes. So Eric, welcome. Please take it away.
All right, thank you. Thank you, Dan. Can everyone hear me okay? Dan, can you hear me?
I can.
You're doing good.
Apologies for the light in my face. My blinds got a little gap in them, but well, thank you everyone for coming today and sticking with this conference, which is going to be really great. So, like Dan said, the use of the title of my talk is the use of small unmanned aerial vehicles to evaluate rock slope stability and assess performance of rock bolts on inaccessible slopes. So we're going to talk about two case studies today. My name is Eric Zorn, graduated from Pitt a number of times over the last 2 decades, and the co-collaborators for this study were some colleagues at DeGoya Gray, PennDOT, and also Gannett Fleming. So first thing we're going to talk about, this is a photogram. Really, it's to talk about the use of technology, specifically photogrammetry, to help us collect data and do work better. So what is photogrammetry? And then we're going to talk about what are we investigating, and then go through the different steps. So step 1 is always going to be your reconnaissance, both desktop and field. And then step 2, the UAV flight planning and data acquisition. Step 3, creating your digital outcrop, so to speak, from which you're going to work. And step 4, identifying your hazards, such as falling blocks for rockfall simulation programs like CRISP, and then your wedge, plane, and toppling failures in your HOEK-BRAY STEREONET analysis, and undercutting, corrosion, or general damage on rock bolts and other built structures. Then step 5, which is usually the most important step, what did you learn and how can you improve? So what is photogrammetry? So when we take a photo, a single photo of our world, we remove that third dimension. We create a flat photograph. So in order to restore that depth, photogrammetry allows us to, if you take 2 or more photographs of the same object from different angles, you can start to get that depth of field back, restore that 3D quality. And if you multiply this by 1,000 or 10,000 times on a large outcrop, now you can create big 3-dimensional point clouds in true color, and it really creates what I was calling before the digital outcrop. And the hazard we're talking about here, first is rockfall hazards. So this picture here is a common sight all over the Appalachians, Western Pennsylvania. Blocks of rock on the shoulder of the road and some cones to make sure people don't hit them. And if you look up at most of these vertical, subvertical rock faces, you'll see wedges and spaces where rocks used to be that are no longer there. So like I was saying before, the first step is always going to be familiarizing yourself with your site where you're going to be working on your desktop in the office. Pull up your maps, look at Google Earth, do a drive-by in Google Earth on Street View, look at your outcrop, and then go pull up some stratigraphic columns, place yourself in the column and figure out where you are. And you can usually identify some features you can expect to see in the field. In this case, this first study in Glassport, PA, along the river, we can see that we're in the Morgantown sandstone, is the main stratigraphic unit on this vertical rock face. And right away, we see we're overlain and underlain by coal-bearing clay rocks, which always creates problems. So you get undercutting of this massive Morgantown sandstone, which removes vertical support. you start to lose support at the bottom of the sandstone outcrop. And then second, which is common in these large, wide, deep valleys of the Appalachians, you get something called valley stress relief because you've removed lateral support. So you get these slope face parallel subvertical valley stress relief joints, which create sliding wedges, blocks, slabs. And then third, when you have coal-bearing clay rocks or weak rocks at the top of your resistant unit, you can start to erode those away and get water infiltration behind the slope face, and which will, over the course of a few freeze-thaw cycles, you can separate slabs from the slope. So once you do get out in the field, you start setting up for your field survey and acquiring your data, you have to get up close and personal with the rock outcrop, start to lay down your survey ground control points to georeference your 3D point cloud back in the office. And you execute your programmed engineered flight. And then as time allows, and traffic control allows, and if there's features that you want to get some more detail of to show the client later on, you can get what I like to call glamour shots, things like this, precariously balanced rocks, if you will. So here's I've mentioned a programmed pre-planned flight plan a number of times here, and this is what it looks like. So in this case, where we're turning photogrammetry on its side, as opposed to looking down, we're looking sideways. So we do more of a stacked flight plan, one flight line on top of the other, and you're moving back and forth, taking pictures of the rock outcrop of the slope face at different angles, and then you're integrating all these together to create your three-dimensional point cloud. And this is what you get when you create your digital outcrop. This is not a photo, so to speak. This is a true color point cloud. And I'll just rotate through this a little bit so you can see the level of detail, actually seeing behind objects. We'll take a little detour through the shrubbery there. And you can really start to quantify volumes and sizes from the 3D point cloud. So the first thing you're going to do with this is pick the low-hanging fruit, what I like to call the blocks that are going to fall eventually. And you can quantify the volume, the mass, the height, and then potential energy and the lithology, and all this gets plugged into ROCKFALL simulation programs like the Colorado ROCKFALL program. And the second aspect of this analysis is going to be your mapping your discontinuities. So now you're getting into the structural geology aspect of it, where you're mapping your planar features via some specialized software if you have it. But really, you're just fitting planes and line traces to planes that aren't visible. And since this is a georeferenced point cloud, the planes are also correctly oriented in space. So once you've exhaustively gone through your digital outcrop and picked the planes and traces and all the features you want to represent in your kinematic analysis, you bring your STEREONETs, your stereographic space into it. And if you've been in a structural geology class or a rock mechanics class, you've likely seen STEREONETs before. And a STEREONET enables you to take three-dimensional planar features and project them onto a two-dimensional polar coordinate system like this, and not lose any of that orientation, that critical orientation data that we're after. So in this case, we see two sets of fractures the main bedding set, which is sub-horizontal, the fracture sets, which are more or less sub-vertical, and then also you impose the orientation, the average orientation of the slope face itself, which becomes a critical input to the analysis. So you can convert those planes into poles, which are a little easier on the eye, and really bring out any clustering that you have and enable you to pick out those fracture sets. And like I said, here we see 2 fracture sets in the bedding set. And right away, you take your statistics, your average strike and your average dip, and you make a little table, and right away, before you even and dips, and specifically the fracture set 2 dips in the same direction, but not quite as steeply. So this is the HOEK-BRAY STEREONET analysis portion, where you start to break your stereographic space into zones, which help you focus on the type of discontinuity, the type of failure that you want to quantify. And on the previous slide, I showed the fracture set 2 and the slope face were going to adversely interact with each other, and this is why. You see the little inset graphic in the lower right here, where the discontinuity itself dips in the same direction, but not quite as steeply. You get what's called a daylight. The plane itself daylights in the slope and creates a sliding plane failure. And the shaded area here is the area of concern. This is the area of the stereographic space where it's likely to encounter. If you have discontinuities that fall in this space, you should be concerned about sliding planes. And then toppling blocks is similar, but where you have a similar strike between the discontinuity itself and the slope face, but the dip is a high angle dip, but in the opposite direction of the slope face. So you get toppling blocks and toppling slabs. And in this case, we only have one little dot here in this area of concern, which may very well be an outlier itself. So not too much concern over toppling blocks. And the third main failure mode you can look at is the intersection of the fractures with other fracture sets. And you get sliding wedges if you have fractures intersecting with each other and creating wedges that then fall out of the slope. In this case, you need to be careful looking at this because this plot looks very severe, as if you have a very severe hazard of sliding wedges, but some of these fractures may not be spatially able to interact with each other. So you should really, if you think you have a large risk of sliding wedge failures, you should break your slope face into zones, and so that you can just look at discontinuities that are spatially able to interact with each other. So I mentioned 2 case studies. This is the second case study, and so we're going to change our focus from the performance of an engineered rock slope above a major roadway to the performance of engineered improvements below a major roadway. So this is the Boulevard of the Allies Duquesne Bluff rock bolt inventory and assessment. And back in the early 2000s, PennDOT and Gannett Fleming wanted to improve the performance of this elevated roadway above the Duquesne Bluff by installing pin piles through the piers down into the rock, and also installing rock bolts with dental concrete to keep the rock slope below the roadway intact and from falling apart. So this is the rock bolt and dental concrete layout in a drawing view, and then if we bring in the actual a photo of the slope, ortho photo of the slope overlay, and this is how it looks in real life. So you see the dental concrete row kind of down below the piers, and then the rock bolts scattered around in a pattern on the rock face. So what are we looking
at? 15 minutes. So,
all right, thanks, Dan. Bulls, they had to re-drill something, an anchor, anchors that are almost exposed, undercut dental concrete, and also the pier. And then kind of the worst case scenario where you've got a fully exposed rock bolt and plate with no bearing surface left. So a simple actionable list of defects that require attention is the optimum deliverable from a study like this. Prioritize and provide to the client or a contractor for repair. So in conclusion, what did we learn? That there is no replacement for the engineer geologist understanding or ground truthing, and the UAV is only a tool for data collection, but it's a very important tool and powerful tool. You get an immense amount of data that would be otherwise inaccessible. And you must plan and program your flights meticulously, but be prepared to modify or expand your data acquisition to infill. On a well-exposed rock face, photogrammetry is an economical alternative to airborne LiDAR. And some of the benefits include drastically increased safety, decreased field time, and a visual record of the site for reference in the future. And how can we improve the workflow? You can treat large slopes with a zoned approach to spatially classify risk. Your time of day and time of year are important for maximizing quality data to reduce shadows and vegetation cover. And also, practice makes perfect. So it's hard to get out onto sites like this sometimes. So every chance we get, we love to do it. So we thank PennDOT and Gannett for these opportunities. And thank you. And any questions or comments, bring them up now, or you can email me at email shown there. Thank you very much.
Thank you, Eric. There's a question from Henry Mongrain, says, when you find rock faults, what can be done about them?
Pardon me? I missed it.
When you find rock faults, what can be done about them?
When you find rock faults, rock falls or rock faults?
Faults.
Faults. What can be done about them? Well, the most important step is knowing that they're there and that they're a risk. And then kind of where you go from there depends on who is at risk. Is it a risk to assets, a risk to people? Is it out in the middle of nowhere? It's not going to hurt anybody or anything if it falls. But what can be done about them? A variety of things. You can engineer solutions like rock bolts, rock netting, descaling, things like that. Or, you can take a wait and see approach, let it fall, let it fail, clean it up later. So, I mean, what can be done about them? Pretty much anything. And it really all depends on the client's needs and wants and really who's at risk and what is at risk.
Tony has two questions. I'm going to ask the second one, and I think that after that we'll have to wrap up.
Okay.
But Tony says the images are fantastic. What is the resolution when the outcrop is wet?
What is the resolution when the outcrop is wet? I mean, the resolution is not going to change, but what might happen if you get a wet outcrop and dark spots and color changes and things like that is the rock face, the interpretation in some way, but it's kind of the resolution itself is not going to change, but a lot of color changes can complicate interpretation sometimes. Is that what you meant?
I think so.
Yes, that is. Thank you.
Okay.
And if we have any time at the end, we can come back and address some of these other questions. But hope everyone will join me in thanking Eric for a really excellent presentation. I mean, as Tony said, that there's just beautiful images. It's really helpful for us understanding what's going on.